Thank you, Dr. Roy, and thank you, attendees, for joining this seminar. I will talk about the research on adaptive value of information using a method called TopK ranking contextual bandits for information selection systems and some of the extensions to this method. Before I begin, I'd like to recognize Michael and Konstantinos who worked on this research I'm presenting here today. Michael and Konstantinos are PhD students from the Department of Mathematics at UMD College Park. Next slide, please. So let's start with the motivation for this work. Today, sensor technology is advancing and computing devices and sensors are used widespread everywhere, every day by just about everyone. Consequently, the data generated by these devices is growing at a ever expanding rate. Data-driven decision making has become a norm. However, decision makers are faced with growing information sources, but there's no commensurate growth in time, resources, and human cognitive abilities to leverage the full information. So information overload has become a new real problem, and it can pose an adverse effect with a serious consequences. Abundant information in dynamic and heterogeneous nature also adds to these challenges. So these challenges leads to a question, which information is of value in consuming? Next slide.
Jade, it's taking some time. I don't know why. Let's see. It's not moving to the next slides. Let me see if I have to stop sharing, then do that. Sorry for the inconvenience. Let me share again. Let's see. Yes, it works.
All right. So for high value information assets, as determined by the users, the best selection policy is to filter out the information and that is of little use or not interest to the user. And emphasize on delivering high value information faster and more accurately. It should be also informed by the accurate context around the situations and the goals. Also filter out the information that does not add any substantial value toward the goals, and also eliminate any superfluous or redundant information. Next slide.
There is something happening. It's not allowing me to move. Next slides. I don't know what's the fundamental problem here. Okay. Maybe I need to do not full screen, maybe. Let me do that. So, yeah. Zed, is it okay if I keep it like this?
I'm okay.
Okay, move forward.
Yep.
Next slide, right? Or this is the right slide?
Next slide, please.
Yes, we are at slide number 4. Go ahead.
All right. So to this end, a variety of expert systems have been developed in recent decades as a mean for coping with this cognitive and systematic information overload problems. Here, the context data provide an insight regarding the usefulness and prioritization among the information objects tailored to a user. When the context attributes are used, the prioritization strategy can be based on the probabilities of high and low value information. And this high and low value of the information object is predicted from the context regarding the user. The user state or the user environment and the responses to an item or the other related items and its use. So the context information serves as a design variables for the probability of the value judgment on the potential use of the information objects. Next slide, please. Okay, so the TopK ranking deep contextual bandit is an approach to determine k number of objects to a recommended user, to recommend to a user. So what are the specific problems to address from this method? The first, determining a single best object is simpler than multiple objects. When the system needs to provide a set of most relevant or user-preferred information objects, the potential candidates for this set of information becomes a power set. And evaluating each collection of the power sets is combinatorial, and it becomes NP-hard. In reward-based learning, such as reinforcement learning, the prediction based on context assumes linearity on the utility or reward and the context. This design may not be suitable when this assumption does not meet, especially when the context data inherently takes complex and a very high dimensional form. So we developed a novel approach for selecting an optimal set of objects given complex and high dimensional contextual input. But first, some preliminary on multi-arm bandits and related works. So the multi-arm bandit is a decision problem where multiple arms, quote unquote, are presented from which one is to choose an arm. This is a reinforcement learning method that learns to match dynamically an object to the user's interest from the previously seen behaviors. From there, the contextual multi-arm bandit uses a multi-arm bandit strategy with incorporating the context variable. It often uses a linear combination, which has been shown to be sufficient, very simple and very straightforward in implementation in most cases. However, it can result in unsatisfactory performance when this linearity assumption is invalid. Now, the deep neural network has been successful in approximating nonlinear value functions and also proven to be a very powerful function approximator. And lastly, the approach for selecting a set of arms in MAB framework is proposed by Chen et al. By approximation oracle method. And also learning to rank technique is a ranking-based information retrieval technique for selecting multiple items from the user query or the user preference. Next slide. So we approach the problem as a contextual multi-arm bandit for ranking, given historical interactions and the context. Using the context features and the estimated rewards, say that there are k objects with the k object with the highest rewards are predicted by running successive multi-arm bandit algorithm at each round. I'm going to use the terms object, information objects, and items interchangeably here. Then exploration and exploitation scheme is implemented to suggest or recommend an item or object. The MAB scheme selects a single object with the highest reward after excluding the previously selected arm, and this is done k times successively. Now, once the reward from the selected k arms observed, then DNN is trained over these observed data to learn the relationship between the context and reward. And at the next round, new object is introduced, and this process repeats iteratively over time. Next slide. The next slide, please.
Jade, I can see the experimentation.
Okay.
See the experimentation?
Yeah, okay, good. So we experimented our approach on two contrasting classification data sets from the UCI machine learning data repository in the lab simulation, just to see how the algorithm works. So we set these data set as a reinforcement learning process and implemented this TopK ranking, the contextual bandit method. And we evaluated the learning performances on three of the exploitation schemes, including epsilon greedy with positive epsilon, and also epsilon greedy with decaying epsilon over time, and also Thompson sampling algorithm. Also, a linear regression and neural linear method was used, and these methods provides the baseline against the DNN method, where these two methods really do not do any exploration. It selects purely greedy. We buried the Bandit parameters and neural net tuning parameters for DNN, including like number of arms, number of neurons in the network layers, and to represent the real world scenarios, we added a scaled noise term to the reward functions. Next slide, please. So the first experiment was on the mushroom data. The goal here is to choose K mushrooms that are edible from a collection of N mushrooms, given that each trial based on their features and past experience. The data set included the labels on whether the mushroom is edible or poisonous, with 22 distinct characteristic features for each mushroom. The reward noise term is scaled by 1/2, and the cumulative reward is clearly the number of correctly selected edible mushrooms amongst these N mushrooms. This experiment is to provide a baseline result where in this case, clearly the data set, the context is well structured, they're easily interpretable, with somewhat moderate dimensionality and very simple reward structure. Next slide, please. So shown here, just two selected cumulative regret plots from and we ran several simulation scenarios. But overall, across the result, the linear model-based algorithms performed well consistently, with the linear regression being the best, and then the neural linear the best. And just note that these were the one that did not really do any explorations. Now, Bayesian Thompson sampling method performed the worst except for the random guess. The increase in the neurons and neural network did not appear to improve the performance. Now, although there was no a priori reason to believe that the relations between the reward and the context for each mushroom is linear, but the linear method actually is shown to be performing better than the deep neural net. Next slide, please. But now let's look at the second experiment. So we set up a bandit problem using the digit samples from MNIST data sets. Clearly the MNIST data set is to provide a context in very high dimensional features. The image includes an integer digit between 0 and 9. And here the goal is to identify the TopK largest integers from n number of images that's shown. The image features are used as a context input, and the reward is the sum of the value of the integers inferred from the images feature vectors. Next, please. So in this experiment, we saw that over time, the linear model begins to underperform compared to the neural linear, neural net with epsilon greedy and Thompson sampling. Thompson sampling method did not show better performance compared to neural linear and epsilon greedy. In particular, the epsilon greedy, again with the DNN, implemented at decaying rate over time showed the best performance. Neural linear performed better than linear method. And with the increased size of neurons in the neural net, epsilon greedy with DNN outperformed the neural linear over time. Since the neural linear does not implement any bandit exploitation scheme, the learning was very limited to previously observed optimum set. The learning performance could depend on the choice of the neural net tuning parameters. It needs further investigation on how these parameters can affect the learning performance. Next slide, please. So now let's look at some approaches to extend this method for enhancing the accuracy and overall applications. At this time, these has been just a theoretical investigation so far. So we have been working with the single user learning or potentially many users' experiences, but these learnings in aggregate are independent from one another. We want to extend this into collaborative learning or collaborative filtering to be more precise. Collaborative filtering is not a new concept. In fact, it is very widely applied in many applications. Basically, the learning the user preference is inferred based on a collection of other users' preferences for an item or objects, and the similar profiles of the features will make recommendations to a particular user. Especially this specific user is new. If this specific user is new or a new object is introduced which has not been seen in the past, collaborative filtering has shown to have very high prediction accuracy, namely for data sparsity or a cold start problem in reinforcement learning. And there are variations in the approaches for the collaborative filtering, but one of the most successful methods is the model-based approach. The model-based collaborative filtering uses matrix factorization, which is reducing the matrix dimensions into the characterization of the objects or objects and items, matrices, and the user features. And using the matrices of these latent factors in relation to the real matrix, the high correspondence between the user item latent factors predicts the user preference or user selections. Next slide, please. So how do we apply factorization in the multibanding method? So here's one approach proposed by Wang et al. As an example, and we'll present a general framework around this. And this is for a single information object selection, and we will ignore the set selection as we have done through the TopK ranking at this moment. So say we have n number of users and m number of items denoted as D like earlier. And we'll set up the latent factor vectors for each user and also item as theta and nu, which are to be estimated from this regularized quadratic laws equations. Now also note that the binary real-world matrix can also be factorized using methods such as the link predictions. Next slide, please. So for the context on the items and also the users, and here we're going to denote that as X and Z. Along with these latent factors nu and epsilon for the contextual multi-arm bandit, we can further incorporate the similarity or relations among the users. And we do this with the relational graph G, where G consists of V and E. V is the vertices representing the users, and E is the edge representing the relations, the influence, similarity, proximity between the users. And this graph G is parameterized into a matrix W. Now, lastly, we also consider loosening the reward on items to change with time, because the user interest in an item may vary in time, rather than being just fixed and constant. This dynamic nature of the interest or the need for an item by the users may evolve with the situation in time, or the needs can change once the item has been consumed. And the reward can be also sequential in nature, depending on what was consumed before. So there are many situations that this time invariant reward function, or rather time variant reward function may be more appropriate, or even produce accurate results. So to allow a time variant reward, we incorporate drift term, which is to be included in the reward model, and we model this drift term as a Gaussian random walk with a Markov random process. So finally, all these reward functions will capture all these terms. And then we will implement the MAB exploration and exploitation schema here. Next slide, please. Now, coming back to these multiple item selections, recommendations. So again, instead of recommending a single information object in each iterations, again, our interest is looking at filtering and recommending for multiple information objects. So, currently the ranking was the approach that we chose for our algorithm, but there had been some concerns, including concerns using this K, ranking method, or the learning to rank method. These concerns include the ranking may deliver the objects that are too similar, it lacks diversity, and etc. So combinatorial method for evaluating this superset, which I mentioned is to be really NP hard before. We are considering revisiting that, and again, because it was NPR, hence the reason why we were using the ranking. But again, I think we are going to look at some other method, including Chen et al. And we like to revisit this combinatorial contextual MNB method. Next slide, please. So in summary, we propose this method for systematic selection of information objects in ranked order, learning from the historical responses, and optimizing the potential use of the information according to the context of the user state, and the environments. And we propose an approach that learns k-most user relevant information objects from a given finite set as a TopK ranking on contextual multi-arm bandit algorithm, combining with deep learning approach. The proposed method was evaluated in two contrasting data and demonstrated this method learned to predict and recommend the objects very well, correctly over time. And also we investigate on how we can build upon this TopK deep contextual bandit method and enhance to implement collaborative filtering method. Some of the key methods we studied here were the representation of latent factors between the user and the items, and combining the observed context from the item and the user context, and representation of the user-item interactions, and also in between user relations using graphical method, and perhaps you may look at a bipartite graph in the future. And also lastly, the time variant reward component, as well as we want to revisit the combinatorial bandit method. Next slide, please. So For the future work, we plan to look at the impact of the DNA structures and the hyperparameters for the neural net for optimizing the performance more closely. And also we will look at how robust the models are under the high level noise at from varying degrees. We're going to continue investigating on extending this method toward the collaborative filtering techniques and other considerations discussed here. And again, we will turn to deep learning for this nonlinearity or very complex and high-dimensional latent features. And potentially, we may look into some hybrid model that combines the factorizations and the deep learning in this collaborative filtering method. Okay, next slide, please. Actually, that's all I have. Is there any questions?
Thank you. Thank you, Dr. Freeman, for the excellent talk. Any questions from the audience? Please unmute yourself and you can ask questions directly.
Hello, Dr. Freeman. This is Jian Wang from UMBC. Thanks for the great talk. I'm not a researcher in this area, but I'm trying to understand what's the context do you mean here in your study? Because context might mean different things. For example, in your applications, you use the mushroom. You have features. What's the context in that example could mean? Thank you.
Yeah. So actually the context will be the representing the features of those mushrooms, the characteristics of the mushrooms. So the context could be for any items or any information objects. Could be I think I'm just trying to give a quick examples. If you're looking at some sort of the imagery or for the imagery, it's actually context is basically the imagery, the features is basically what is being fed. But just very rudimentary basic example of the context about say that you're if it is some sort of the item for shopping or the movies in recommender system, it could be something like the genre of the movie. It could be something that is the some sort of classification of certain things about that item, some characteristic about the items. Does that help you?
Yeah, it helps. When we normally do data mining, we do feature engineering and feature selection. Feature selection, we select from the 20 features. We select most important 5 features. Feature engineering, we do some changes with features to do like PCA to find important ones. So for your study, the context is more similar to context feature engineering or engine feature selection.
Yes, correct.
Okay, thanks.
Thank you. Thank you, Gianno. Any other questions? So, Dr. Freeman, I have a quick question. You described the talk with this mushroom application, but any specific military application you are exploring and applying these fundamental technique to that context? If you could enlighten us on that, that would be great.
Yes. So as I mentioned, that the motivation was the the necessity to reduce the information overload, and clearly in the battlefield information environment is and clearly not immune to these whole information overload problems. So the application of this valuable information, which we have a couple of other threads in this research portfolio in our branch, is really kind of developing this expert systems to smartly select and filter and select, and as well as prioritize the information objects. So that's the motivation behind this. And also this speaks to also the sort of some other type of valuable information application is the and also the information sharing. So which information to be shared under the different constraints, whether it is a network constraint or if it is just again purely a cognitive load. This falls into that whole portfolio of how we can smartly utilize the resources, whether it's a network or whether it's a cognitive bandwidth, how we can efficiently share the information or disseminate information given this the information saturated environment.
Thank you, Dr. Freeman. So just to follow up, so in that case, like your reward function might change over the time. Like, can you consider like quality of the information or quality of service as a reward function based on that specific application?
So that's a very good question. So quality of information is also a obviously very important aspect in information sharing, and I know there's a very good discussions that had happened before my time here regarding how does the quality information fits into the value of information. What we are looking at here is really not accounting for the quality of information and recognizing the fact that this QoI really has to be a part of the information filtering and the prioritization, the systematic selection in that aspect as well.
Got it. Thank you. Thank you very much. Any other questions to Dr. Freeman? Please feel free to unmute yourself and ask any question. Okay, if not, then let me stop sharing the screen. Let me has been stopped already. Anyway, if there is no more question, Dr. Freeman, thank you. Thank you very much for your talk, and thank you for taking time to come forward and delivering your seminar on the ArtIAMAS seminar series. Thank you very much.
Thank you. And if anybody have any questions, please feel free to reach out to me. And also, I think I showed it the last slide that we're always looking for a good researchers to collaborate. And if anybody interested in this sort of work, then also please contact me as well. Thanks.
Thank you. Thank you. That concludes our seminar. Thank you. Thank you very much, everyone.
Thank you.